Okay. Welcome to week 7 of Case Studies in Scientific Literacy and week 3 in the climate change module of the course. We've talked about Earth's climate system and components of climate. We started talking last week about what alters the system. So we talked about some natural drivers of global change. Evolution of the atmosphere, volcanic activity, Milankovitch cycles, and solar irradiance. And those things cause changes in the reflectivity of the Earth, greenhouse gases by speeding up or slowing down the carbon cycle and the water cycle. Volcanic activity causes atmospheric dust and aerosols. So these are natural drivers of climate change. And I wanted to address a question that we had last week. So one of the things that we talked about, one of the lines of evidence that climate is changing, is that there's less ice on the planet. And here we have a picture of ice and snow in the Arctic. But the question was, we've seen evidence that maybe the Antarctic is actually increasing in ice. And in fact, there's this article, a NASA study from about a year ago. Mass gains of Antarctic sheet ice are greater than losses. Now, if you actually go to this article, which I would suggest that you do, it's based on one of the many ways of measuring ice. This is a really interesting website. And again, I would encourage you to go to this website. Actually, I think I have it up now. But this website goes through a variety of climate myths. And one of them is that Antarctica is gaining ice. So I'd encourage you to go to this website and look at, there's many, many more arguments, climate myths, and they kind of do a rebuttal of those. But one of the things that is happening is that sea ice is indeed increasing. So ozone layers in the Antarctic have dropped. And as a result, there's more cooling in the atmosphere, there's increased winds, and so a lot more open water is actually freezing. Also, the Southern Ocean is becoming a little fresher, especially at the top, from rain, snowfall, and melt of ice. And that means that there's less ocean mixing, and so there's less melted sea ice. But that's sea ice. If we look at land ice, things might be a little different story. So this is Antarctica, including East Antarctica. So sea ice or land ice does appear to maybe be increasing in Eastern Antarctica. On the other hand, Western Antarctica is losing land ice pretty rapidly. And so overall, Antarctica is losing land ice, although sea ice might be increasing. And if we add in Antarctica and Greenland, we see that the mass of land ice is decreasing pretty rapidly. So that was in answer to last week's question. And of course, we also know that Antarctic sea ice Arctic sea ice is declining. In fact, this just came out. Arctic sea ice minimum ties second lowest on record. And we can watch a little video of that. If I hit the right button. So Arctic sea ice is declining, and we've just had a record decline in Arctic sea ice. Okay, to get to the main point of today, we're going to talk about anthropogenic drivers of climate change. So the first day, we looked at a variety of lines of evidence that climate and the globe is changing. What do these all have in common? If I put all those graphs back up there again, what do they all have in common? Anyone? Okay. They're accelerating. All the graphs are going up, and a lot of them are going way up, like a little dip, a little ski jump thing at the end, right? So for example, here's a temperature graph, and starting in 1880, and we see it's increasing and then kind of starts to increase even more. So what is causing this relatively recent and accelerating rise in temperature and all those other things that we talked about? Well, it could be one of the natural drivers of change, right? Could be volcanic activity. It could be solar irradiance. Could be greenhouse gases warming up the Earth. So let's take a look at these. So volcanic activity. We talked about the fact that when there's a large eruption, the temperature of the global temperature actually dips a little bit because these volcanoes are spewing dust and aerosols into the atmosphere, which block solar irradiance. So maybe we just haven't had enough volcanoes erupting lately. And that's one of the arguments that people say, well, it's the lack of volcanic activity. Or vice versa, they say, well, volcanoes are spewing greenhouse gases, which they do. They spew out CO2, but not very much. And in fact, if we look at, so this is basically, I'm not going to explain the details of what this really means, but these are volcanic eruptions and changes in how much irradiance reach the Earth. And the idea that we haven't had recent volcanic eruptions is not true. We have. And maybe I'll show this next week. If we looked at the amount of CO2 spewed out by volcanoes, it's like a tiny bit compared to the CO2 being emitted from other things on the Earth. What about solar irradiance? Maybe this global warming is just due to changes in the sun. And that's one of the explanations that people have. It's the sun. And if we look at solar irradiance since 1600s, it does seem to have increased. Okay, well, maybe that's valid. But if we look more recently, since 1978, solar irradiance is kind of maybe flat, maybe going down a little bit. Sunspots is another thing people say. That's, kind of, it's been higher, and maybe it's decreasing. So it's the sun is maybe not a good reason. Also, if we look at solar irradiance and temperature, those graphs clearly are not matching up. So how about greenhouse gases? Maybe what keeps our Earth warm, those greenhouse gases are increasing. And that's where this record of carbon dioxide from Mauna Loa Observatory comes in. So this is the longest CO2 record that humans have for the Earth. And these people, Lean and Rind, and this is one of many similar papers, they wanted to know if they could statistically look at what is driving surface temperatures, global temperatures. So they looked at, it's the sun. They looked at volcanic activity. They also looked at El Nino, which I didn't mention, but that's another thing that people claim is changing the Earth's climate. Versus, it's us, basically. So they did some statistics and looked at how important solar activity, volcanic activity, El Nino, or anthropogenic forcing, so that's us, is on changing global temperature. And for the anthropogenic forcing, they actually specifically broke it out. Greenhouse gases that humans release, aerosols that humans release, and land use changes that might result in changes in Earth reflectivity, or the fact that we're putting dust on snow and changing reflectivity. So what they did was they looked at the contributions or the forcings of these per decade from 1979 to 2005. And they found that, for example, El Nino actually caused the global temperature to decrease a little bit over that time period. Volcanic aerosols cause the temperature to increase a little bit. So changes in solar irradiance actually maybe caused a slight decline in global temperature. And anthropogenic forcing was responsible for most of the net global temperature change over this time period. Now, it actually came out to 112%. So clearly there's some heat that the Earth should have warmed up even more than it did that is probably going into, for example, the oceans. Okay. Now they also looked at these different types of anthropogenic forcing. So aerosols we're putting into the environment actually caused a decrease in global temperature. Changes in land use kind of flatline. But greenhouse gases are the primary anthropogenic forcing of the temperature changes. So that's what their statistics say. Here's just another way of looking at it. HADCRUT, I'm not sure how you're supposed to say that, but is a measurement of global temperature. It's one of the models. And they looked at over different time periods, the effects of solar changes, volcanic changes, El Nino changes, and anthropogenic changes. And again, we see that it's us, basically, that's causing these changes in surface temperature. And they came to the conclusion that none of the natural processes can account for the overall warming trend in global surface temperatures. In the 100 years from 1905 to 2005, the temperature trends produced by all three natural influences are at least an order of magnitude smaller than the observed surface trend. So it is not the sun, it's not volcanoes, it's not El Nino. Evidence suggests that it is us. And again, greenhouse gases appear to be really important. Here's another way of looking at it. Those same people collaborated with a bunch of other people. So here's Rind and Lean again. And they looked just at solar irradiance as a natural forcer, so they didn't include aerosols or volcanoes or El Nino. So they looked at aerosols that we're putting into the environment, actually had a negative effect, land use changes, but it's these greenhouse gases, CO2, so carbon dioxide, nitrous oxide, and methane that seem to be doing most of the anthropogenic forcing. So those guys. So let's talk a little bit more about these human influences and greenhouse gases. If we go back and look at some history, actually, so in 1824, Joseph Fourier described how the atmosphere keeps the Earth warm. Like, that's pretty cool. And this Swedish guy, Arrhenius, he's sort of famous in chemistry and physiology because he described how chemical reaction rates speed up with temperature, which is really important. But he also developed a model of the greenhouse effect way back in 1896. So he predicted that periods of glaciation were explained by this greenhouse effect or lack of. And he predicted that if carbon dioxide doubled, global temperature would increase. This is way back in 1896. And then we have Dr. Charles Keeling, who was a geochemist, and he developed an instrument that could measure carbon dioxide really accurately and quickly. And he went camping in the Sierra Nevadas and was bringing his instrument along and measuring carbon dioxide, and apparently it was increasing. And he was like, whoa, that's crazy. So he got some money to establish this observatory on top of Mauna Loa in 1958, which is 2 miles above sea level. And they have been continuously recording carbon dioxide since he put this up in 1958. Interestingly, NSF in the 1960s stopped funding it because they said, oh, this is just routine, who cares? They probably wished that they hadn't done that. But anyway, so it's now the longest record of carbon dioxide in the world. So this is it. This is our record starting in 1958. And this just in, carbon dioxide levels have reached the highest ever, 404 parts per million. If we go back and look at what it was, so when he started recording, it was under 320. Now we're at 404. And Climate Central just tweeted this yesterday. So you know I'm giving you new information. I don't tweet, but I found this online. So Climate Central said carbon dioxide just hit its annual minimum at Mauna Loa Observatory and failed to dip below 400 parts per million. This has never happened before, ever. So we've been up high before. We've been above 400, but this year it didn't dip back down below 400 like it usually does. Okay, so let's talk about this annual minimum. Like, why does it dip down? This is just kind of a fun fact. It doesn't really. So if we look at a little bit of that long graph a little more closely, we see that it goes in waves. So what's that about? Any ideas? snowfall. So it's not snowfall, but it is something that happens on an annual basis. Oh. So in the spring, plants use some of that carbon dioxide that's in the atmosphere. In the fall, they decay and release carbon dioxide. And here, so Mauna Loa is in the northern hemisphere. So that tracks with, spring and fall in the northern hemisphere. If we had one in the southern hemisphere, it would be with their seasons. But we actually see this cycle more in the northern hemisphere because there are more land masses and therefore more plants to grow and die. So that's just kind of an interesting tidbit. Okay, so we have Mauna Loa, and we also can look at carbon dioxide levels based on ice cores from hundreds of thousands of years ago. So here we have, this line keeps going up past 400 now. So how do we know that this is caused by us? Maybe it's something else. It's not volcanoes. Okay, but what is it? Well, we could look, for example, at the global population. So as the population of the world has increased, global CO2 emissions have also increased. So that could be why there's more carbon dioxide in the atmosphere. The Industrial Revolution. Okay, that started at about, who knows their history, 1760s around. And actually, if we look at, so they've combined ice core data and Mauna Loa. If, the Industrial Revolution started about 1760s, carbon dioxide in the atmosphere has risen about 33% just since then. Okay, so it could be population, Industrial Revolution, could be people, right? And here's just another way of looking at, we have atmospheric CO2 levels, and we have CO2 emitted by humans calculated back, and clearly those are both increasing. Okay. I love this website. There's like a dozen, have you guys seen this? There's several dozen, correlation is not causation. So, number of people who drown by falling into a pool, and films by with Nicolas Cage. Clearly there's no relationship, at least we hope not. So correlation, so population, Industrial Revolution, correlation isn't good enough reason to say that we're the cause. So that's where carbon isotopes come in. So this is one way that we know that the CO2 being put into the atmosphere is from us. So there are 3 natural isotopes of carbon in the atmosphere. We have carbon-12, which is fairly light, and that's most of the carbon dioxide in the atmosphere. We have carbon-13, a little bit, and carbon-14, a teeny tiny bit, and it's primarily formed in the way upper stratosphere by, and it's radioactive. So it has a half-life. So if we look at our world, the atmosphere has mostly carbon-12. It has some carbon-13 and very, very, very little carbon-14. The oceans are about the same ratios of carbon-12, 13, and 14. Vegetation, though, is enriched in carbon-12. And that's because it's the lighter molecule. Plants tend to take it up more easily than the heavier molecules, 13 or 14. So what does that have to do with anything? Fossil fuels are derived primarily from plant material. So they are also going to be enriched in carbon-12 compared to the atmosphere. And they're going to have virtually no carbon-14 because they're thousands of years old, and all that carbon-14, if there was any, has decayed and is gone. It's turned into carbon-12. So we can look at our atmosphere and the changes in our atmosphere of carbon-14 and carbon-13 in relation to that carbon-12. So fossil fuels, again, are going to be really, really depleted in carbon-14. It's all decayed. They're going to be depleted in carbon-13 because they're made from plants. The atmosphere is, so if we look at trends in, so CO2 levels are increasing. Globally, carbon-14 ratios are decreasing. Carbon-13 is decreasing because these two are getting basically swamped out by all that additional carbon-12 going into the atmosphere from our fossil fuels, which are only carbon-12. And for whatever reason, this is called the Seuss effect. It's not the Dr. Seuss, it's another Dr. Seuss. But the fact that atmospheric carbon-12 or carbon-14 and carbon-13 are decreasing, I guess was named by, or figured out by this guy, Dr. Seuss. And we can also see, for example, here we have global CO2 increasing, and we have a downward trend in the ratio or amount of carbon-13 in the atmosphere. We can even see, so carbon-14 ratios are highly localized. So again, I said it's mainly produced in the kind of high stratosphere, but it's what is there is getting swamped out by the carbon-12 that's being produced from burning of fossil fuels, and that swamping out is even more pronounced at over areas that are highly populated and using a lot of fossil fuels. Cool. So there's this website where you can go and look at your favorite place in the world and look at the carbon-13 ratios and basically see how polluted it is with fossil fuels, right? Because these areas, if there's less and less C13, there's more, it's being swamped out by more C12. So I chose Key Biscayne, but you can, I'll post this website, and you guys can go look at your favorite location. Okay, so human influences, CO2, what about these other greenhouse gases? How do they contribute to climate change? Oh, so anthropogenic contribution, I forgot that I was segueing into this. So fossil fuel use seems to be where a lot of the CO2 is coming from, but land use changes are also important. So we've seen fossil fuel use increase and temperatures increase. There's actually a little bit of a kind of an offset. So as fossil fuel use increases, there's kind of a lag time of about 30 years, 10 to 30 years. And we can actually see, so this is carbon dioxide produced or put into the atmosphere, and we can actually see blips resulting from things like World War II and the stock market crash and September 11. So these little blips in our use of fossil fuels will actually show up, or changes in our economy actually show up in carbon produced and put into the atmosphere. And so, for example, here's the US. Our use is increasing. China is increasing. It's actually pretty interesting. How are we doing on time? I'll see if this will play and if you guys can actually see it.
Extremely dangerous questions, because with our present knowledge we have no idea what would happen. Even now, man may be unwittingly changing the world's climate through the waste products of his civilization. Due to our release through factories and automobiles every year of more than 6 billion tons of carbon dioxide, which helps air absorb heat from the sun, our atmosphere seems to be getting warmer.
This is bad?
Well, it's been calculated a few degrees rise in the Earth's temperature would melt the polar ice caps. And if this happens, an inland sea would fill a good portion of the Mississippi Valley. Tourists in glass-bottom boats would be viewing the drowned towers of Miami through 150 feet of tropical water. For in weather, we're not only dealing with forces of a far greater variety than even the atomic physicist encounters, but with life itself.
This is a little movie from 1958 where they talk about how fossil fuel use and so on is going to change the world. It's fairly entertaining, but fairly accurate given, how long ago it was. Okay, land use change. So this shows CO2 emissions from land use change. Now, how does land use change contribute to CO2 emissions, and what does that even mean? So I mention this because deforestation, for example, can be really important in contributing to CO2 emissions. So as we cut down forests, those trees are not there to sequester carbon from the atmosphere, and also a lot of times those forests are going to be burned. So that is going to be released into the atmosphere. So climate or land use change contributes to, I see different values, but maybe about 20% of the anthropogenic change in climate. And we can look at it over time. So here we have, this is fossil fuel use and cement manufacture. So cement actually produces a lot of CO2 emissions. You can actually measure this, it's pretty impressive. So land use change in the tropics is relatively important. Land use change everywhere else it's there, but compared to fossil fuel use is not as important. But still, clearly, land use change is important. And if we look at, this is another kind of geopolitical, interesting way of looking at things. If we look at per capita greenhouse gas emissions, including land use change, we can see which countries are producing less CO2 and which are producing more. Okay, so one of the things we talked about in a previous lecture was changes in the carbon budget or carbon cycle. So it speeds up or slows down over time. So another way of looking at it is that we are changing this carbon cycle. So the black lines, the numbers don't really matter, but the black lines are pre-industrial, so pre-industrial revolution, and the red things are anthropogenic contributions to this climate or carbon cycle. So we can see, for example, that fossil fuel use is increasing or emitting CO2 to the atmosphere. Land use change is emitting CO2 to the atmosphere. So these are things that weren't happening before us. So what is causing this CO2 increase? And what about other greenhouse gases? So I've just been talking about CO2. What about some of these other things that we might be putting into the atmosphere? I said that greenhouse gases include water vapor and methane and nitrous oxide and chlorofluorocarbons. So what about those? We're also producing those. And if we look at, for example, methane, this is in parts per billion, and we do some math that figures out how much radiative forcing is due to methane. We see that indeed it's fairly important, but not as important as carbon dioxide. And nitrous oxide, again, this is parts per billion, so it's a lot less than carbon dioxide. And the relative forcing, is smaller, but there's not as much. But methane, for example, is more potent than CO2. So there's a tiny, tiny bit of it in the atmosphere, and it's causing this much increase in global temperature. Nitrous oxide is is even more potent as a warming molecule than carbon dioxide, but there's not very much of it. Chlorofluorocarbons are really, really potent. I didn't have a graph of that one, but so these other greenhouse gases are also important, and we're also putting these into the atmosphere. If we look at our greenhouse gas emissions, here's, so mostly carbon dioxide, but methane, nitrous oxide, and then the things like the chlorofluorocarbons are also important. So we know that methane has been increasing in the atmosphere. Methane, where is it coming from? What's that? Cows, yes. So here we have livestock farts, basically. It's coming from landfills, decaying vegetation. A lot of it is coming from worldwide production of rice and the material that rots away after rice is harvested. Natural gas leaks. So biofuels, which I find pretty interesting, biomass burning, so that's deforestation and biomass. But biofuel combustion. So we think biofuels are really good because they produce less CO2, but on the other hand, they might produce some methane. So these greenhouse gases are contributing to this human-enhanced greenhouse effect. And as we have learned, global temperature is increasing, and that is resulting in some of these other global changes. Warming oceans, shrinking ice sheets, glacial retreat. The CO2 is contributing to ocean acidification, extreme weather events. So we've looked at fossil fuel use, greenhouse gases, land use change as anthropogenic drivers of climate change. And next week, we will look at basically what are the predictions for the future. We'll talk about climate models, because I think those are really important in understanding where we're going and what we might need to do to prevent a worst case scenario. And then I'll talk about a few ecological, economic, and social impacts that we're experiencing now or that are predicted to happen in the future. Are there any questions? Yes.
With the 404 like parts per million
Yeah.
carbon dioxide, isn't that kind of like, I was kind of reading a thing that was saying that like since we are at that like level that we're kind of like past the like no turning back point.
Yeah, I'll talk more about that next week, but it does, once you get to a point, it is kind of a runaway because there's so many positive feedback loops, right? I mean, we can't, we have models, we have statistical models, mathematical models. I don't think we can totally predict the future, but I will definitely talk about that next week. Okay.